Let us now aim at the next central question when it comes to CFD-DEM simulations. What is the physics behind the coupling of the DEM and a CFD simulator? And how is the coupling actually done in a computer code? First, let us start with the fundamental physics behind momentum coupling. In this case, we look at the drag force that acts on the particles, and that is also acting on the fluid in the opposite direction. This force is the simplest momentum coupling force besides many others, e.g. the lift force. To understand drag force calculations, we start with the momentum balance equation of the fluid. Earlier, we have already shown this equation, and we have also talked in our polydispersity unit on the permeability of a granular material. Well, this permeability is related to the volumetric coupling force phi that quantifies the strength of the coupling. Phi is here underlined with the red transparent box. Phi can be calculated from a sum over all particles I in our RVE with volume delta V. Note that Wi is a weight between 0 and unity and that it quantifies how much particle I contributes to a specific RVE. This should now make the connection of an individual drag force to the fluid's momentum equation clear to you. Hence, we can next ask the question, what is the force on a particle in a dense suspension that has a relative velocity u compared to the particle? The situation that we want to consider is shown here on the right, and the particle of interest is shaded here in red. A large research community has worked on theoretical expressions for this drag force and, fortunately, has agreed on the form that you see here on the bottom. The force calculation consists of two components. The first one is the Stokes limit, i.e. at 0 particle Reynolds number and in an infinitely dilute system, so if only the red particle would be present in that flow domain. This Stokes limit can be again split up into a prefactor that contains only physical parameters and the term here in blue. US is the superficial velocity difference between the fluid and the particles. The second term here, shown in red, is a dimensionless drag force F. This quantity F needs to be correlated with some other dimensionless quantities, as we will see later. However, before we do this, there is one important thing. F must approach unity in the Stokes limit for obvious reasons. Any correlation for F that does not do this is less helpful. Let us now continue with the next important result, which can be obtained when replacing the weighted sum over the particles in our fluid momentum balance with a term proportional to phi p. Making some other assumptions, specifically that all particles feel the same fluid speed and that the Sauter mean diameter is representative of the particle population, we arrive at this important result. Thus we see that F directly impacts the pressure gradient in a bed of particles. Clearly, the quantity F is the key dimensionless quantity to be predicted. And we now want to look at different correlations for F that are available in literature. The first one is the famous Ergun equation. It is available in almost every textbook in the field of particle technology. As you can see, the first term is linear in phi p for small phi p values for which the denominator is close to unity. The second term is linear in the Reynolds numbers, i.e. it vanishes in the limit of slow flows. And this is important. The ergon equation cannot be used for dilute flows since the Stokes limit, meaning f equals 1, is not predicted for slow flows in which this second term vanishes. We note in passing that the Reynolds number is defined with the superficial velocity and not the phase velocity. Also, the Sauter mean diameter is used as the appropriate average diameter in case of a polydispersed granular flow. The next expression that was first published by a Dutch group around Professor van der Heuvel approaches the correct limit of f equals 1 in case phi p approaches 0. You see this here. However, it does not predict the effect of the Reynolds number. Such a term was later added by Beetstra et al. As you see in the final correlation that I mentioned here on this slide. This work of Beetstra, by the way, she is a successful female researcher now applying her knowledge in industry, is widely used in the community and has almost 1,000 citations. Let us now plot these correlations as a function of the particle volume fraction. This is exactly what is done here on this slide with a minor tweak. We plot the product of f and 1 minus phi p squared, as you see here on the label for the y-axis. This is because, as you might have noticed on the previous slide, the leading term in the correlation that are then exactly linear in phi p, which is very helpful, for example, for visualization purposes. What can be observed is that the van der Heuvel correlation is in perfect agreement with PR CFD data. PR refers to particle resolved, which was generated for the limit of vanishing, so 0 Reynolds number. The correlation of ergon is plotted for a Reynolds number of 10, for which it has an offset of approximately unity. Note that this offset of course vanishes if we would use a Reynolds number of 0 in this ergon correlation, as was the case for the PR-CFD simulations. Also, we see that the correlation of Beetstra evaluated for a Reynolds number of 10 yields considerably larger f values compared to that of the van der Heuvel correlation, which is valid in the limit of vanishing Reynolds number. Thus, the Reynolds number effect is important, which is why the correlation of Beetstra was such a big leap forward in the history of drag correlations. To round up our discussion of the drag correlation, I have prepared a plot of the original, so unscaled f values for you. Please note the log scaled y-axis in this plot. Again, you see close agreement of all the correlations with particle resolved CFD data. However, what is important is that f is approximately 10 already at a moderately dense particle packing of 0.4. Thus, the drag on a particle in a moderately dense bed is already 10 times higher than that on an isolated particle. If we follow the curve further, we see that f approaches huge values beyond the close-back limit, the latter being approximately 0.6 particle volume fraction. As you can see, the drag then becomes quickly 50 to 100 times higher than that in the dilute limit. In practice, that means that fluid flow through the packing is virtually choked off, and fluid will attempt to flow through the most dilute regions of a particle bed, e.g. through cracks or regions that are simply less dense. Last, you can also observe the high sensitivity of F with respect to the particle volume fraction at high values of phi p. This essentially is important when we talk about the algorithmic details of the coupling algorithm. Just keep in mind for now that small changes of the particle concentration may result in large changes of the drag force.